focused on the regression,
Okay.
like what is a regression, and then the two major types, the lasso and ridge, when they
Okay.
both are differently applicable, and how to choose the test set and training set. And so
Okay.
mainly the focus was there on the regression.
Okay. Fine. That's good. So today I'll be starting with another topic called dimensionality reduction. Okay. Let me share my screen. Yeah. Hope it's visible. Yeah. Is my screen visible?
Yes, sir.
Okay. Yeah. Fine. So yeah. What do you think about this title called multivariate data analysis? What is multivariate data analysis? What is univariate? What is multivariate? Anyone? What is univariate? What is multivariate? No idea. Okay, so what do you mean by features and what do I mean by labels and tags? Let's take the example of the iris dataset where I classify flowers species based on some features, right? So what is the feature there and what is the target that I'm going to predict? And was it a classification or regression test? I have these three questions. Can anyone answer?
For the features, can we say it's like the attributes which are used to define something
Yeah, that is correct.
to
And yeah,
uniquely?
yeah, unique features. Yeah. So like let's say height of the petal, width of the petal, and sepal and so on.
Yes.
So that was for iris. And was it a classification or regression task that we did before?
Classification is mainly to uh, decide some labels, and
Mm.
based on the label, whatever the characteristics are matching, we are
Mm.
dividing the things accordingly.
Mm, not
That is what
dividing.
the class, like
Yeah.
categorizing the things.
Yes,
Yes.
yes, yes, that is correct. Yeah. In the regression, it's all continuous real value numbers,
Yes.
right? Okay. So if you think about features, okay, there are, let's say in that iris example, you had four different features. Let's say petal width, sepal width, petal height, and sepal height. So there are four different features for classifying into its corresponding species. What if there was a single feature, just say petal height or petal width? Okay, that case is what I would call univariate data analysis. You just have a single feature, you just have a single target that you have to predict. Okay, if it goes more than one, okay, then it's called multivariate data analysis. So in the iris case, what data analysis paradigm are we dealing with? Univariate or multivariate?
It is multivariant because there are four different features on which we are focusing and then we are classifying.
Yes. So it's a multivariate data analysis case, and that is what we're going to look at today. Okay. Yeah. So multivariate data analysis. What do you mean by data analysis? Is you get insights into trends, patterns, and relationships. Okay. These are different plots. Okay, this is a scatter plot. This is a distribution plot. Okay, what do you see here? Why, I mean, just looking at this picture, what do you get? So each color represents the corresponding species, and this is an example. Um, let's say example that you have. Let's say a five examples that you have with four features and one target. Okay, looking at this plot, what do you think? What is the insight that we get? So each so this is sepal length versus sepal length. This is sepal width versus sepal length. You have four features, so there are like eight different combinations that you can get to see. So I mean not eight, 16. How do you visualize this? I mean, how do you what insight do you get anyone? Okay, let me explain. So if you look at this plot, okay, it will give you the distribution of sepal length among three different species. Okay, this is sepal length versus sepal length. This is sepal width, petal length, and petal width. Petal width. Among these four, okay, which feature do you think is able to separate these species more? How separated? So among these four, let me know. Which feature is able to separate these species more just by looking at it?
Um, Petal width and length has the least overlapping over the values.
Yes, yes. So those features are, I would say, very important.
Yeah,
Okay, these
distinguishing
features,
one. Hmm.
yeah, yeah. So these are what we call as discriminative features, where it is helpful in discriminating among the species. But when you go to multivariate data analysis case, you won't have just single features, right? You will have interaction between two features, interaction between three features, interaction between all four features. In this case, I'm also considering interaction between two features. So this is an interaction between sepal length and sepal length. Okay. And again, look at these scatter plots. Based on the scatter plots, which combination, list out one or two, okay? Which combination do you think, again, best separates these three species?
Sepal width and petal width.
Sepal width and yeah, that is also good. Petal length and sepal width is also good. So yeah, okay. But can we visualize three features together, like sepal length, width? That also we can do something like this, okay? 3D visualization. But can we visualize all four together? That is the question here. Can we? 3D we can. Four dimension, can we visualize? Can we visualize in four dimensions? This is 2D. This is 3D. Can I move to 4D?
That will give us a more clarity, I think.
But can we visualize? There are only three dimensions that we can see. Fourth
Hmm.
dimension, we. So what do you do? What you can do? Let's say you have 10 different features. We can't visualize in 10D. That is not possible for us. Okay. So what we can do is reduce the dimension for this. Let's say from 4, I can reduce to 3 and look at it like this. Or I can even reduce to 2 and look at it like this. That is what I can do to get more insights. Okay. And this is where dimensionality reduction comes into the picture. So I'm reducing the dimension of the features from 4 to 2 or 4 to 3 or whatever n to 3 or 2. Okay. So this is where principal component analysis comes into the picture. Okay. Uh, so it is analysis of data to identify patterns. So that is what data analysis is. Find good patterns to reduce the dimension. Okay. But one thing that we have to make sure is something called minimal loss of information. Okay. Because if you reduce from 4 to 3, you also lose information. Okay. There won't be 100%. When you reduce from 4 to 3, you can't go back from 3 to 4, like get the same features again. So I need an algorithm which has minimal loss of information and that can represent my data well. Okay. So whatever characteristics I see in 2D or 3D, same trends, characteristics should also be seen in, let's say, 4 dimensions or 10 dimensions and so on. This is the objective of PCA or principal component analysis. Okay. Any doubts till now? Okay. No doubts. Moving on to the algorithm specifics. This is the overall approach of how PCA is done. Okay. You take the whole data set without labels. Without labels, meaning I won't have the classes or species or any other regression problem. I won't have the label. Okay. You compute means for every dimension, compute covariance matrix. Uh, so calculating mean, getting covariance matrix was all taught in the linear algebra class, right? What can anyone explain what is covariance matrix? Covariance matrix, eigenvalues, eigenvectors. These terms have been introduced before, right? What do I mean by these terms? Linear algebra was taught, right? The previous classes. Okay. Okay, let me go through it in the coming slides. But yeah, ultimately what you want to do is transform the data set into newer subspace from 3 dimensions to 2 dimensions. That is what I'm going to do now. Okay. So let's say this is my data set. Okay. I have two different classes. This is some random data set that I've taken. I have 40 different data points. I have three features, two labels, let's say class 1 and class 2. Okay. Problem of multivariate analysis is visualization. So I'm starting with a simple 3D example. Okay. And what I want to do this is convert this 3D into 2D, drop one dimension. This is what my goal of doing PCA is, principal component analysis. Okay. So first we start with computing the mean vector. Okay. So how many dimensions do we have? First question, how many dimensions do we have? How many dimensions or how many features do we have? How many features I have? Three, right? It's in 3D. So I have three features. So you will have three different mean. Okay, across 40 samples, across each feature, I will calculate the average. Okay, I'll start with that. And then I'll get the covariance matrix. Okay, if you look at this plot, both the plots have same average, that is 100. But one is having higher variance, one is having lesser variance. Okay, and you can see the difference, how it's distributed. Higher variance plot is like this, lower variance plot is like this. So I want to see how for each samples the variance is across different features. Okay, this is for single univariate case. If you go to multivariate case, you have to calculate something called covariance, which explains how two different variables are related. Let's say you have two different variables, okay, x and y. X is like this, y is like this, and this is how my data will look like. Same opposite case, low variance for y. So as you can see, it's not too much across y-axis, but it has a lot of variance across x-axis, so that's why it's spread out like this. And this is my covariance matrix. Okay, you get it? And then there is positive covariance, where the data set is slightly, increasing. It's an increasing form, the line. Okay, negative covariance, it's a decreasing. Okay, slope like this. Zero covariance, you can't find any correlation between two variables. It will be randomly distributed here and there. Okay. So when you look at the covariance matrix, you can explain how two different variables are related. It's for two variables. It can be n number of variables. You can calculate the covariance matrix. Okay. Any doubts in this? How spread out my data is? That is what I want to find using the covariance matrix. Any doubts? Okay. Moving on. I have computed the mean, computed the covariance matrix. Next comes eigenvalues and eigenvectors. Okay. Eigenvalues, they'll tell you how spread out my data is. If it's spread out like this, see, my eigenvalue is higher. If it's spread out very thin like this, my eigenvalue is lower. Same case, you get eigenvalues, higher eigenvalue, lower eigenvalue. If it's spread out like this, again, more in this direction, less in this direction. And this is for my data set. So if I have three different features, I have three eigenvalues and three eigenvectors. Eigenvectors will give you the direction of spread, in which direction the spread is. So you can see the direction and you can also see the magnitude. Okay. Now I have three eigenvalues, three eigenvectors. I want to convert from 3D to 2D. What should I do now? And the eigenvalues and eigenvectors are calculated from the covariance matrix that you calculated in the previous slide. I have three eigenvalues, three eigenvectors. I want to convert from 3D to 2D. What will I do? And also remember, I want to capture maximum spread in my data. Capture the direction and value with maximum spread. Okay, anyone? So what I'll do is I'll take the top two eigenvalues, top two eigenvectors, and I'll drop one. That is what I'll do. Okay. This is called matrix factorization. I think this is a bit too much, but yeah, we'll skip this part. See, this is what I'm doing. You have a large table, five different features. You have a covariance matrix, 5 cross 5. Okay. You get eigenvalues and eigenvectors. Okay. And you arrange it from big to small. Let's say I want to convert 5D to 2D. I'll take these two, convert it into a smaller table that I can visualize like this in 2D. Okay. This is the overall flow that I'm going to do. And this is what I've done. Okay. You have samples like this from 3D. I've converted to 2D. If I want to do linear regression on top of this, will it work? And do you think it has converted this 3D to 2D quite well? Just look at these two and let me know. Just visualize, just by visualization, just check if it has converted it properly or not. I think it's quite good. Okay. Somewhat information is preserved. You can see the blue dots are here. You can see the blue dots are here. You can see the red dots here. You can see the red dots here. Okay. There is some sort of separation that is being maintained when you convert from 3D to 2D. But I would say if you convert back from 2D to 3D, you will lose some information. That is for sure. 100% reconstruction is never possible in PCA most of the times. Okay. You have some loss, but the loss should be minimal. Okay. So what you can do, you can summarize the information contained in large tables. You can easily visualize it in 3D or 2D. And it need not be just 3D or 2D. Okay. You can convert from 100 features to, let's say, 10 features and then do linear regression and so on. But selecting this K, you have some criteria, how many components that we should select. If it's just for visualization, you can select K as 3 or 2. Or if you do want to do further build machine learning models on top of PCA, you can take how many ever components as desired. Okay. Then moving on to partial least squares. The PCA case that we saw before is called an unsupervised method. Okay. Unsupervised in the sense you are not using any information or labels at all. Okay. But PLS, partial least squares, is a supervised technique. You try to explain the data with an explanatory variable or the labels. You also have information on the labels here. You see, this is, I have data like this. Okay. I'm converting into using PCA. You can see here the group is well separated, but here it's not that much separated properly. But if I also give information that this blue point belongs to group one, this group two, this orange points belong to group two, if I also give that information into take that information into consideration, you can see it's well separated when converting from 3D to 2D. This is what I want. So this is a supervised technique. You should remember PCA is unsupervised, PLS is supervised. Okay. Differences here, no label information or target information is used. I'm not giving any groups or species as such. Here I'm using the information. That's it. And you can visualize different, let's say, features. Okay. This is PCA in 2 dimensions. You can use a correlation plot to visualize like this feature. This is my eigenvector for high jump and eigenvalue. This is my eigenvector for pole vault. There are different features. Okay. And this is your typical biplot and VIP scores where you check what are the important features that you have. Okay. Ultimately, PLS is an algorithm that you can use for classification, I mean regression using label information, but PCA mostly it's for visualization. But again, you should also in this you can also see some percentages here, right? What do these percentages mean? Any idea? Like I think about information loss, think about this percentage, go through the steps and think clearly what do these percentages mean actually.
Does it signify that how much percentage of data has been dimensionally reduced to get the more focused important data?
Uh, you're almost there. I wouldn't say how much data. Yeah, you can say it like that because how much percentage of data I'm capturing effectively. Okay.
Yes.
So
Hmm.
if you keep increasing dimensions, what will happen? Let's say now I'm visualizing in 2D, now it's 3D. Obviously, the information captured will be more. In 1 dimension, just 41% of the data is being captured. If I increase from 1 to 2, 41 plus 18 percentage. So it's almost 59% information is being captured. These are
Hmm.
things that are also called explain variants, but I'll explain it in the tutorial tomorrow. But yeah, if you increase to 3 dimensions, it might jump from 59 to let's say 70 percentage. Okay, totally
Hmm.
how many features are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You have 10 different features. If I just do PCA from let's say 10, again, let's say I'm converting it back to 10 because I've selected K as 10, then obviously 100% information will be captured. But there is also a trade-off. Let's say if I right now with 2 dimensions, it's 59%. With 3 dimensions, I'm already reaching 90%. Okay. With four, I'm reaching 99. If I keep increasing to 5, 6, it's 99.1, 99.2. But that 1 percentage uh, doesn't matter much, I would say. Let's say with four components alone, I'm capturing 95%. then I'm happy. I don't need to keep increasing my components. If I keep increasing components, again, a lot of computation will be involved and so on. I'm happy with 4 components. So based on these values only, you will check what number of components should I select. And this, again, there is no like single rule. Okay. Each data set is different. You have to see how much variance is being captured. Okay. 59 is very low. So what I would say is you can't come to any conclusion based on this plot. Let's say if you do 3D and visualize and it's 90%, yeah, you can come to conclusions like these features are important and so on. Okay. Yeah. Here it's 8.2, 8.3. Obviously, it's not enough. Okay. And you can see that there is some separation. But in reality, when it goes to like 10 dimensions, there is actually no separation. You see why coming to conclusions based on PCA is dangerous. Here you can think like different classes are being separated somewhat. But when you actual in 10 dimensions, it's actually not separated at all. So this is one of the problems with PCA. There are better techniques right now like UMAP, TSNE, and so on. Okay. Better techniques that can do dimensional reduction better than PCA. Those are all some advanced concepts that is out of the scope for this course, but PCA in general is a lot helpful for visualization, reducing the number of components. And one more thing where we need to reduce components is, let's say, in this case, sepal length and sepal width are almost same for this particular plant or something. Then you can actually drop one. You don't need to keep this again. So that is one more thing where you remove unnecessary features. That is also one thing. Summarizing PLS, it is supervised method. It combines the power of principal component analysis and multiple regression. Okay. Highest predictive power meaning, if I also take into consider my labels, it is being able to predict well, good accuracy. You can think of it like that. And also it is recognizing the direction that is actually most predictive. Even though a particular eigenvector or an eigenvalue can explain the data, that direction might not be the most predictive. It might not be useful for doing the prediction. So if you use PLS, it will recognize the eigenvector and eigenvalue. That is actually the most predictive. Yeah. Uh, that's it about dimensionality reduction for today. Any questions, any doubts, I will be happy to answer. Tomorrow I'll be taking a tutorial on PC and PLS hands-on Python session. Okay. Yeah. Give you all some time to take these things into consideration. Yeah. And if you have any doubts, I can clear. Okay, then if you don't have any doubts, then we can end the class now. Thank you all for attending. See you all tomorrow.
Thank you,
Bye.
sir.
Yeah, thank you.